All right, gonna do number 33. So I've got integral x minus 3 over the quantity x squared plus 2x plus 4, that quantity squared. All right, so I have a linear expression over an irreducible quadratic, and so we looked at one of these before we actually started partial fractions, and we said that we could do this if we try to let u be the denominator and take the derivative here and then try and make our linear expression on the top match up with this. So I need a 2x plus 2 on the top. So what I do is I multiply the top and bottom by 2, which leaves me with a 1/2 out here. The 2 goes through. I get 2x, minus 6. That was it. The 2 has to distribute to both terms, 2x minus 6. And then over the x squared plus 2x plus 4 squared dx. Now at this point, I need to make that a 2x plus 2 right here. So I realize I have a hidden 0 right here. It's a minus 6, so I'm going to add 2 and subtract 2. What I had done is instead of putting minus 6, I put minus 3 again. See, I had a minus 6 here, not a minus 3. And that changes everything. So that allows me now to split this right there. In this first integral, I have u squared on the bottom, there's the derivative on top, and then up top over here, I put these constants together, and that'll be a new integral. So we've got 1/2 integral, and then I've got the 2x plus 2, and then over x squared plus 2x plus 4 squared dx. And then here I put these together, it's negative 8. And I bring it out 1/2, it's going to give me a negative 4, because negative 8 over 2 is negative 4. Integral, then there's a 1 up there, x squared plus 2x plus 4 squared dx. Okay, so now at this point, this integral is pretty clear. We've got u squared on the bottom, you've got du up here, you've got 1/2. So we're really just trying to figure out what the antiderivative of 1 over u squared is, so u to the negative 2 du. And that's just going to be negative 1 over 2u. That's the antiderivative here. And u in this case is that. So this first integral, the answer, is going to be negative 1 over 2 times u, but u is x squared plus 2x plus 4. All right, so that integral is done. Now over here, minus 4, integral of 1 over x squared plus 2x plus 4 squared dx. I need to try and figure out how I handle an irreducible quadratic with a constant on top, but in addition to that, it's squared. So what we did in the past is we actually did a completing of the square on that quadratic, which is what I'll do over here. And then I'll hope for the best after that. So take my x squared plus 2x plus 4. I take half of 2, which is 2 over 2, which is 1. And then I take that answer and I square it, which is also 1. So I go x squared plus 2x. Then I take this 1, I add it, I subtract it, and then I still had a plus 4 there. So when I put those together, the first 3 become an x plus 1 squared, and then these two together become plus 3. So this integral now becomes negative 4 integral 1 over, in parentheses, x plus 1 squared plus 3, but all of that was being squared dx. And now you might be thinking arctan here, but the problem is, even though you have like variable squared plus constant squared, the whole thing's being squared, and that arctan doesn't work for that. So I will make a basic substitution right now. I'm going to make a substitution that u is x plus 1, du is dx, and if I do that, I can rewrite this integral as -4 integral 1 over, then this becomes u squared plus 3 squared du. So all that does is kind of cleans this up a little bit, makes it a little nicer to look at. And then for this one, you have to do something we did in class, which is a little bit sneaky, is to rewrite this as u squared plus 3, that quantity to the 4th power du. And the reason we do that is because we have a trig substitution we can use for this if it's under a root. So we just kind of rewrite it so it looks like it's under a root. And the trig substitution we use when we have variable squared plus constant squared is a tan theta. And in this case, u will be equal to a, which is root 3 tangent theta. Then du is root 3 secant squared theta, d theta. And the square root of u squared plus 3 is equal to root 3 secant theta. So now I'm ready to rewrite this. And I'll do it back up here. So at this point, I have 1 over, and then this square root right here is root 3 secant theta. So root 3 secant theta, but then that quantity to the 4th power, then times du, but du is this. So root 3 secant squared theta d theta. And now I actually have to raise this to the 4th power, so I have to do root 3 times root 3 times root 3 times root 3, which will give you 9. So these together are 3, these together are 3, multiply 9. So I have a 9 on the bottom here. And then up here, just a root 3. So I'm going to bring out of this integral a root 3 on top and a 9 on the bottom. And then I still have integral. Now I have secant to the 4th power, and I have secant squared. That leaves me with 1 secant squared in the bottom. And we've seen that before. 1 over secant squared is the same as cosine squared on top. And we know what to do with that because it's an even power of cosine, so we come in with the half angle identity. When we do that, we know we're going to get a 1/2 that we're going to pull out, so I'm going to change this to 4/18. Actually, I can reduce this to 2/9. And then integral, and then it was 1 plus cosine 2 theta d theta. We've integrated that so many times. Let me erase this here. So remember, this is still part of my answer. It's in the front of everything. So I have 2 root 3 over 9, and then antiderivative of 1 with respect to theta is theta. Antiderivative of cosine 2 theta is 1/2 sine 2 theta plus a constant. And then this right here, we use double angle identity, and then we rewrite it as 2 sine theta cosine theta, and then the 2 and the 1/2 go away. So my next line should be 2 root 3 over 9 times theta plus sine theta cosine theta plus c. And then I go through and I need to make a reference triangle. And the reference triangle will come off of this information right here. So I have u over root 3 is tangent theta. And then I can get this. See, theta, u, root 3, this side's square root of u squared plus 3. Also, taking arctangent on both sides, I know that theta is equal to arctangent of u over root 3. So I've got everything I need to rewrite this. So this is negative 2 root 3 over 9, and then this theta, which is going to be arctangent of u over root 3. And then I have plus sine theta, don't need this, sine theta, which is u over, what is it, root u squared plus 3 off my triangle, cosine theta, which is root 3 over square root of u squared plus 3, and then that's it, and plus c. And then we have to replace all of our u's with x plus 1. We should be there. So negative 2 root 3 over 9. And then we have arctangent of x plus 1 over root 3. And then plus x plus 1. Oh yeah, this, well, I'll leave the root 3 here. Times root 3. And then on the bottom, we can put these two together, which means all we're going to get is this without the root. So u squared plus 3. So u is x plus 1 squared plus 3. Close the parentheses, plus c. And then you could multiply this through here to here and have that in the very beginning. So let's go ahead and write that out. That should be our final result. So this times this, negative 2 root 3 over 9, arctangent x plus 1 over root 3, and then this times this. Notice that this root 3 here and this root 3 come together. When they come together, they become a 3. 3 over 9 leaves a 3 on the bottom, so I get negative 2/3 times what was still up here, x plus 1, and then what was down here, which was in parentheses, x plus 1 squared plus 3. And all that plus c. All right, double check that. Yay, okay, that's it. That's number 33. Kind of a messy problem there. Okay, number 35. Integral square root of x over x minus 4. And they give you a hint here. They say, make a substitution to express the integrand as a rational function and then evaluate. So right now we don't really have anything in any of our techniques that really looks like we could handle this, but they're giving us a hint. So let's use the hint, and then we'll know later on this is something we might be able to try. So u is equal to root x. If that's going to be u, we got to figure out what x is going to be. So just come over here to this equation, right? Oh, I forgot my dx here. Come over to this equation, and let's square both sides. So I know what x will be. But I also need to figure out what dx is going to be. So what we could do is we could take the derivative here. Du will be equal to the derivative of the square root of x is 1 over 2 root x dx. And then let's try and get dx by itself here. Let's try and isolate this. So I'll multiply both sides by 2 root x. Du equals dx.
Is that supposed to be a negative?
Mm-mm.
You took the derivative of square root of x, isn't x in 1/2, and you took the derivative, so it should be minus 1/2?
Mm-mm. Yes, but then it drops down. That means when it's to negative 1/2,
Yeah.
right? Because this is x to the 1/2. So 1/2 comes out, and then x to the negative 1/2, and then it pops down. So normally we don't like dx to have, when we're going to rewrite dx, we don't want the new expression to have x in it, so we're trying to get everything in terms of u. But in this particular problem, we get lucky, because square root of x is actually u. So this is just 2u du. I did this a long time ago at the beginning of class when we were first doing substitution. And I showed you that, in fact, you could have taken the derivative of this line and done it implicitly. So the derivative of u squared is 2u du. And the derivative of the right side is just dx. And that matches exactly this right here. So you could have done it that way also. Okay, so let's rewrite the integral. We have integral square root of x is going to be u over x, which was u squared minus 4, and then dx, which was 2u du. And then if we multiply the 2u on top here and pull the 2 out, we have a 2 integral u squared over u squared minus 4 du. And we can't do anything simple with that because, well, you can't split it up into two fractions, and so we're stuck. But it's a rational function, and so we go through the steps for partial fractions. And the first step for partial fractions is to check the degree of the numerator and denominator. And in this case, the degrees are the same. And if the degrees are the same, you have to do long division. So I'm going to rewrite this as, or do my long division. I've got u squared on top there, got u squared minus 4 on the outside. And so what I'll do is I'll figure out what I multiply u squared by to get u squared. That's 1. Then I'll multiply, get u squared minus 4. Come through and I'll subtract this row, which changes the signs. I get a remainder of 4. I can't turn u squared into 4, so I'm done. So I put plus 4 over the divisor. So that's this. So this integrand turns into that, and don't forget you have a 2 in front of all of it. So you have 2 integral, and then this turns into this, 1 plus 4 over u squared minus 4 du. And the first part of this integrand is easy. The antiderivative of 1 with respect to u is u, so I can do that. This one's going to require a little more work. So I've got 2u there, plus 2 integral of 4 over u squared minus 4 du. So I split it up, and then I did the antiderivative here. And I'm actually going to pull the 4 out, make that an 8 out here. Make that a 1. And I believe that's a formula right there. That is formula 20. Now the book, what they probably would want you to do for practice here, which you don't have to do on a test or anything like that. You wouldn't have to do it as soon as you get to that point. It's okay. They would want you to take that integral, they would want you to factor the bottom. And then they want you to set up your partial fractions on that. And then go through and play that game, because you have 2 distinct linear factors here. But because this is a formula, I'm going to use that. So this should be equal to 2u plus 8. Formula 20 says times, let's see, 1 over 2 times a. And in this case, a is 2. It's the square root of 4. And then we have natural log of u minus a. So for us, it'll be u minus 2 over u plus 2, or u plus a, so u plus 2. And that's it. So we get 2u plus, let's have 2 natural log of u minus 2 for u plus 2 plus c, plus c. And now what was u? U was square root of x. So 2 root x plus 2 natural log square root of x minus 2 or square root of x plus 2 plus c. All right, let's get to the next one here. What am I on? 37? Okay. So I haven't worked 37 out, so this ought to be interesting. I'm not going to cheat, and I'm not going to look at the solution manual. I'm just going to see how I do with this. X cubed over cube root x squared plus 1 dx. Now this still falls into the section where they say make a substitution first, but they don't tell you what the substitution is. So I'm just go for something here. I don't know why, but I'm going to go with u is x squared plus 1. I'm just going to see what happens. So I know that the derivative is 2x dx, which, do I have a 2x dx? I don't, but if I peel one x off the top, then I do have an x dx right there. And so I need to scale this by 1/2 to get my x dx. So I can rewrite this integral. Okay, what's x squared? Well, I have to come up to this and I have to solve for x squared. So x squared is u minus 1. So I get u minus 1 right here over the cube root of x squared plus 1, which is u, so the cube root of u, times x dx, which is 1/2 du. So here's 1/2 and then du. This one's kind of turning out to be a little too easy. I don't know. So 1/2 integral, I can split this into two fractions. It's u over root 3, or cube root of u, and then minus 1 over cube root of u du. And that I'll just be able to use power rule on, so I don't see why this one's number 37, but oh well. Okay, so this is u to the first power over u to the 1/3 power. So that's u to the 2/3 power. And this is just minus u to the negative 1/3 power du, and then just power rule. So 1/2, and then antiderivative here. I add 1 to that. 2/3 plus 1 is 5/3. In front of it, I need to put 1 over 5/3, so that's 3/5 u to the 5/3. Minus, let's see, I add 1 to this. I get 2/3. 1 over 2/3 is 3/2 u to the 2/3. And then plus c. And now I just replace u with the substitution, which was x squared plus 1. So 3/5 x squared plus 1 to the 5/3 minus 3/2 x squared plus 1 to the 2/3 plus c. And I suppose you could factor stuff out there, but let me just see if this matches up with what they've got. I'm sure they didn't do it this way. 3/10. Yes, they did do it this way. Or, I'm sorry, that is the correct answer. They did a different substitution. Okay. So let's look, now that I've looked at the solutions, let's look at theirs. I mean, we got the same answer. We're going to get the same answer, but let's see their substitution versus this one. The one I did worked, but...
You fit it all on one board.
Yeah, and I got it all in 5 minutes. Theirs goes quick, too. They use the entire denominator. And then they cube both sides. And then they take the derivative here. 3u squared du is equal to 2x dx. Let's see, is that what they do? Yeah, and then, okay, so then when they rewrite things, they still kind of have to do this same thing I did. The denominator, this whole denominator is going to be u. X cubed, you don't have x cubed anywhere. You have x squared. So what you'll do is they rewrite this x cubed as x squared times x, just like we did. And x squared here is u cubed. X squared is u cubed minus 1, right, if you solve this for x squared. And then x dx, right here, x dx is actually, you have to bring the 2 over, so 3/2 u squared du. And then take the 3/2 out, distribute this u through, so you get u to the 5th minus u squared over u du, which is 3/2 integral u to the 4th minus u du. Let's see if I'm on the same page as they are here. Yeah, that's it. And then and then antiderivative of each of these. 3/2, antiderivative there is 1/5 u to the 5th. Antiderivative there is 1/2 u squared, then plus a constant. And then if you change u is this. So let me just show you what this one piece would be. That would be the cube root of x squared plus 1 to the 5th, but that's the same as x squared plus 1 to the 5/3. And that matches up with my answer. And that one over here would be x squared plus 1 to the 2/3. So same result, 2 different substitutions got you to the same answer. But it's worth seeing. 2 more problems, and I'm done with this section. Do you have any questions, or are you good? You good? This next one looks fun. 39. E to the 2x over e to the 2x plus 3e to the x plus 2. Okay, so I'm going to make an observation here that this is the same as e to the x squared over e to the x squared plus 3 times e to the x plus 2 dx. So anytime you see e to the 2x, it's the same as e to the x squared. And I'm going to make a basic substitution right now that u is equal to e to the x. The derivative of that is e to the x dx. So how would this integral look if I were to make that substitution? Well, this would be u squared. This would be u squared. This would be plus 3u and then plus 2. But see, for dx, I need an e to the x dx to match. So what I'll do is, since I have 2 of these up here, I'm actually going to just take one of them and rewrite it out here like this. That's the same exact thing. So now when I look at it, this is no longer u squared, that's just u. That's u squared plus 3u plus 2, and this is du exactly. So I can rewrite the entire integral in terms of u now. It's u over u squared plus 3u plus 2 du. So I have a quadratic, which is underneath a linear expression. So I ask myself, is that reducible or not? Does it factor? It does factor. Since it factors, I'm going to use partial fractions. So I'm going to go ahead and factor the denominator.
I have a question now.
Yeah, go ahead.
Since you peeled off from the e to the x.
Uh-huh.
Okay, never mind. I just realized, I was gonna say, why did she use the one on the bottom? It's because it's 1 over e to the x technically.
What is this?
The middle, the one that says 3 e to the x.
Yeah.
You can use that to
Oh.
manipulate because it's 1 over 3.
Yeah, it can't be pushed out. Okay, so I'm going to rewrite this as u over, and then my factors here, u plus 2, u plus 1, du. And so I have two distinct linear factors. So I get to do my partial fraction game now. And this one should be a shortcut method because I only have two linear expressions. So it should be pretty clean. So here we go. I'm going to rewrite the integrand, and then I'll come back to that integral in a second. For each distinct linear factor, I need a number over the linear factor, like that. And so then I multiply both sides by the LCD. I get u equals a times u plus 1 plus b times u plus 2. And now this is where I can sit here and try and wipe out b to get a, and then wipe out a to get b. So I'm going to let u be equal to -2 first. If I do that, it's going to kill this off. So u is -2, I get -2 equals a times -2 plus 1. So that gives me -2 equals -a, which means a is 2. So I know what a is. Now to get b, I'm going to let u be -1. And then the left side becomes -1. Over here, that's gone. And then I have b -1 plus 2, which is just 1. So b is -1. So I can replace this a with 2. I can replace this b with -1. And now this integral becomes integral of 2 over u plus 2 plus -1 over u plus 1 du. And since these are just linear expressions and I have constants on top, these are going to be natural logs. So 2 pops out, natural log of u plus 2. And then over here, the -1 pops out, natural log of u plus 1 plus c. And what's u? U is e to the x. So this equals 2 natural log e to the x plus 2 minus natural log of e to the x plus 1 plus c. Now, I'm sure that's not what the book has as an answer. My guess is what they did was took this 2 out here and popped that 2 up. Someone knock? I thought I heard a little tap. So natural log of, I'll just put in, I can put this in parentheses. Now let's talk about why I can do this. E to the x plus 2. Well, e to the x can never be negative. And plus 2, that's never going to be a negative number, so I don't need an absolute value because I know it's never going to be negative. So no worries there. Same thing with this. I don't need an absolute value there. So the 2 comes up, all right, and that becomes that squared, and then minus natural log of e to the x plus 1. Oh, I just said I don't need the absolute value, plus a constant. And then you have subtraction between two logs. When you have subtraction between two logs, you can turn it into a single log with division. So, and e to the x plus 2 squared on top, and then e to the x plus 1 on the bottom plus c. I'm going to guess that's what they have here. I would be okay on a test with this, but the rest of it's just algebra to try and match the book. Yep, that's what they have. They have the one on the left side there. Going to do number 41 now. I need a break. integral natural log x squared minus x. Plus 2. So I haven't seen anything like this before. Well, we actually have, but it was a while ago. And you're trying to figure out, you know, is there a basic substitution? No. Is that partial fractions? No. Is it what do you call it? Rational, is it a rational function for partial fractions? No. No trig substitution. Integration by parts, possibly. If we did that, we would have to choose a u and a dv to do our ultraviolet minus voodoo. So I would probably let this whole thing be u, and then dv would be dx, and so you integrate up. And I think that's what's going to happen here. I'm going to try integration by parts. I'm going to let u be natural log of x squared minus x plus 2. I'm going to let dv be dx, and that means v is x, and that means du is the derivative of the natural log of something, which is 1 over that something, times the derivative of what's in here, which is 2x minus 1 dx. So this integral becomes ultraviolet, these two multiplied, so x natural log x squared minus x plus 2 minus integral voodoo. Now voodoo are these two multiplied together, and keep in mind that this 2x minus 1 is really up on top like this. So when you multiply this times this, the x distributes through the top. So you get 2x squared minus x over x squared minus x plus 2 dx. And that is a rational expression. Polynomial divided by a polynomial. The powers are the same, so I've got to do long division first. And this is an irreducible quadratic, so I won't ever be able to factor that, which means that I'm going to have to use that technique where I try and match the du to the top and come in with a hidden 0 and then break it apart and then do completing of the square. And so this is going to be a long problem, which is why it's number 41 probably.
Is this the last one?
This is the last one, yeah.
So you have to use 2 different integration techniques.
Yeah, you're using integration by parts followed by some partial fraction stuff, which is just going to be the long division part, followed by that weird matching massaging game, and then completing the square. And
You might want to save your first.
geez, completed squares. I hope we won't need trig sub for that.
You might want to save.
Yeah, this, I just have to remember this is here. All right, let me do long division over there. 2x squared minus x on the outside, x squared minus x plus 2 here. To turn x squared into this, I need to multiply by 2. So 2, and I get 2x squared minus 2x plus 4. And then I come through, I subtract or change the signs, and these go away. I get x, and then I get minus 4. So my remainder is x minus 4 over x squared minus x plus 2. So this integral right here becomes minus integral 2 plus x minus 4 over x squared minus x plus 2 dx. I can take the antiderivative of 2. That's just going to be 2x. And then I have to figure out what this is. So what I'm going to do is I'm up here, I'm going to write down where I am so far. I have minus then the antiderivative of that, so minus 2x. And then I have, the next part is whatever this is, so minus integral x minus 4 for x squared minus x plus 2 dx. So whatever I get from this, I'll slap it on right there, and that'll be my final answer. So when I'm here, I have a linear expression over a quadratic expression. The quadratic is irreducible because I cannot factor that. When this happens, We let u be the bottom. We take the derivative. 2x minus 1 is what we want. We don't have 2x minus 1. So I come in here and I force a 2 over 2 here. And when I do that, this integral now becomes negative 1/2 integral, distribute the 2 through to both of them, 2x minus 8 over the x squared minus x plus 2 dx. And then I need it to be 2x minus 1. So I have to insert a minus 1 plus 1 here. So right here, I insert minus 1 plus 1 so that it will match this right here. And that will become negative 1/2 integral. So I have the 2x minus 1, that's the first part, and that's going to be over the bottom. And then I'm going to have a separate integral, which I'll still bring the negative 1/2 with me. Oh, forgot my dx. Bring the 1/2 with me, new integral, and it's going to be whatever was left here. So I already used the 2x to minus 1. I have plus 1 minus 7, or minus 8, which is going to be negative 7 over the x squared minus x plus 2 dx. This one right here is just u, and that's du. Perfect, that's just 1 over u du. Antiderivative of that is natural log of u. But u was this. So I can tack that onto my answer up here. Minus 1/2 natural log of x squared minus x plus 2. And now I still have more. I still need to figure out what that one is. So I'll do that right here. I'll pull the negative 7 out. It's going to be 7/2 integral 1 over x squared minus x plus 2 dx. I'm going to complete the square on this one. Ooh, we get to use fractions. All right, I'm going to complete the square there. Okay, so when I complete the square, I take x squared minus x plus 2. The number in front of x is negative 1. I divide it by 2. It's my first number. I take that number, I square it. That gives me 1/4. So I'm going to add and subtract 1/4. X squared minus x plus 1/4 minus 1/4 plus a 2. The first three terms guaranteed a factor to be x and then this number, minus 1/2. And then I have to put these two together. Negative 1/4 plus 2 is the same as negative 1/4 plus 8/4, which is 7/4. So my denominator can be rewritten with this. So x minus 1/2 squared plus 7/4. Ooh, yes. I like it. This is arctan. Got a variable squared plus constant squared. Nothing else happening. So I can make a basic substitution if I want of x minus 1/2. Du is dx. And then this integral becomes 7/2 integral 1 over u squared plus 7/4 du. And I just need to figure out what a is. So a is the square root of that. So a is going to be root 7 over 2. And so this integral right here becomes 7/2 from out front times the formula number 17 for this right here, which is 1 over a, which is 1 over this, so flip that over. Arctangent of u over a. So u over a, but u is this. So u over a, which is root 7 over 2, and they most likely would flip this up and pass the 2 through there, and then we could cancel these 2's. So we get like 7 over root 7 arctangent of 2x minus 1 over root 7. And then you could actually rationalize that. But you take this answer and put it right there, okay, to this, add that to it, plus c. That's it. Yeah, that's it. The only thing they did in the book was a little different, is that these two are the same. So they factored it out, and that left an x minus a half and an f. It's all the same thing, so it's good. All right, so I think that's it for this section. Yeah. Thank goodness, chapter 6 is pretty much over. Cool.